Uh, Deepak Kulkarni is a fellow in advanced packaging at AMD. He's been working on advanced packaging technology development for over 15 years. Prior to AMD, he was the Senior Director of Packaging Yield at Intel. So, Deepak, please proceed. Thank you.
Thank you, Ira. Thank you, Ira, and the MEPTEC team for giving me this opportunity to share some of AMD's thoughts on the chiplet architecture. Today, what I would like to do is start with an introduction to chiplets as we see it, and then dive deep into some of the design optimization activities that we are doing, specifically on the substrate side. So I think the audience here is aware that we've been going through several transformations as it comes to semiconductors. And as we ramp from the PC to the smartphone era, we saw a significant increase in the number of devices and the demand from a computing perspective. What we see going on now is with the advent of the data center and artificial intelligence applications, along with the benefits that 5G architectures provide for connected devices and edge intelligence, we're really seeing another explosion in the demand for compute. And our focus at AMD has been on how do we support this significant increase in demand for high performance computing. To give you a little more background on what we are seeing as far as trends, this is some of the industry analysis that was done recently. And what you see in the graphs above is that both in terms of CPU as well as GPU, we see significant growth in the number of transistors year over year. So in essence, we are continuing to see this exponential demand. And as this exponential demand for compute increases, many cases, these high-end devices require transistor densities and number of transistors that far exceed the current reticle limits. So how do we address this increased demand? One approach that AMD has been driving for several years now is this concept of chiplets. And what this involves essentially is instead of having one monolithic SoC, you divide your overall die into chiplets. And these chiplets, when manufactured through the wafer processing step, result in higher number of yielding units that meet the customer's compute demands. So the first portion that I wanted to highlight over here is that chiplet architecture provides you with a yield benefit and a method for resolving some of the reticle limits that would have limited the number of transistors that you could pack in a particular device. Let me pause here and maybe quickly ask if there are any questions on high level, just what is chiplet architecture and what benefits we see with that.
I don't see any open questions, but thank you.
Okay. So as we evolve this chiplet architecture, I think the other key realization is that it also provides a significant benefit from a design modularity perspective. When you can define these chiplets, not just as multiple similar parts, but functionally different solutions, you are able to then choose for each individual product a set of chiplets that are meeting or catering to the specific demands of that segment. So the number of chiplets as well as the type of chiplets that you can mix and match to achieve your end goal provides a significant design benefit, and that has been the primary focus of this talk over here on chiplets and their design optimization. Now, in terms of substrates and what roles they play in this key architecture change is that as we implement solutions like 3D die stacking or 2.5D elevated fan-out bridge, you see that these packages are becoming more and more complex. And so from a substrate perspective, we need to be able to accommodate higher body size, higher layer count packages. In the past, you could think of it as the package sizes were limited by the largest die that you could pattern and attach. Now that requirement no longer holds. With chiplets, you could have a die complex that far exceeds the reticle limit, and associated with that, you need additional layer count and body size to be able to connect it. These chiplets also are power hungry in the sense that we are continuing to see increase in the power delivery demand for these chiplet architectures. And so providing that power delivery solution through the substrate is another key vector of where design optimization comes in. Lastly, from a data rates perspective, we are continuing to see high-speed I/O requirements continue to grow because these devices and their associated compute power requires that they are connected with fast data rates to other memory buses or other devices on the board. And so we are also seeing the need for fast data rate solutions through the package. Here's a slide on what all of this has meant in terms of the substrate demand. And this is some of the work that has been published by Jan and the TechSearch team. What this essentially shows is that when it comes to substrates, we are seeing a significant demand. And in many years, we have seen the capacity outstripped by the amount of demand we have. And we expect this to continue through the 2023 timeframe as well as 2024. So in addition to looking at this substrate challenge from a technical vectors perspective, we also need to look at it as what can we do to address this demand versus capacity gap. Okay. So now getting into a little more on the details of how we've approached this. Our approach has been to look at this very early in the design phase and walk through some of the choices that we need to make, both from a product performance perspective as well as from a design for manufacturability perspective. So for example, we start our discussions very early in the design phase to talk about the body size that this package can fit in, and that is based on understanding the number of chiplets, what type of power delivery, number of I/O signals that these packages need to have. While we are making those choices on a performance perspective, we are also looking at this from a design for manufacturability perspective and asking the question, what is the minimum body size that all of these things can be fit in? And how can we improve panel utilization? Because the number of units that you can fit on a panel essentially means you get additional capacity for a given product. Similarly, as we continue to fine-tune our design and look at power delivery and signal integrity requirements, we are also looking at optimizing the layer count and the routing density to ensure that this design meets our manufacturability targets. And ultimately, this does translate into a co-optimization of the silicon floor plan along with the package design in order to maximize yields and maximize our ability to improve cost and capacity for these packages. So the key takeaway from this schematic here is really to touch upon the fact that design optimization is not an afterthought, but starts very early on in the concept phase. And there are various stages through the entire design process where we need to continue to work towards improving yield, cost, and capacity.
So a question, two questions that came in,
Sure.
but one is there, you're talking about the substrate optimization, but in general, is there a rough ballpark at what size die makes sense to split up? Is it any size die, or is there like a minimum maximum size that it makes sense to, break into chiplets?
Yeah, that's a very good question. And I think it goes back to this topic that I was talking about with regards to modularity. So if you are looking at this purely from a yield perspective, you could design a set of equations that would say beyond this die size, there is net benefit in splitting because the cost associated with the split or chiplet architecture is lower than the yields and the monolithic SoC that you're going to build. But I think what we are seeing right now is the modularity and ease of reuse of these chiplets also plays a very critical role. And so in that sense, it does become a product and IP specific decision, not necessarily this one number where you say beyond this die size, you must split.
And would the defect density be the most significant driver, or do you think that, well, or actually what you're just saying is the product design really ultimately rules?
Exactly. With the heterogeneous integration, it is not just about achieving the highest yield, but also about enabling different chiplets with different functionality to be mixed and matched.
Thank you.
All right. So to enable this solution that evolves through the entire design phase, what we've been developing is an end-to-end analytics approach where we have inbuilt solvers that are able to take in various different data streams, such as information from the vendors on their size information for panels, as well as our historical yield and process window data, and pricing and capacity information to put together a holistic end-to-end solver that can optimize the size of the package, optimize for yield, as well as optimize for cost and capacity. And I think this is very critical in terms of how we've set it up, that this tool is a learning tool. That is, it isn't a static solution based on one set of data, but continues to evolve and learn as we get additional data that helps us improve its accuracy and predictability. So I'm going to delve a little bit more into the details of how we approach this. And I think the first portion of any learning approach is how do you train this model? And over here, I'm providing a schematic of how we've approached this. We have taken a machine learning approach where we extract design information from these packages and then use that information to then determine with the historical yield data, a training model that can correlate these design parameters with our estimations for yield, price, and capacity. Once this model has been trained, then we can utilize this model for any new product evaluations. As soon as we have some of those design attributes for a new product, we can run it through our inference engine to determine optimal package design. And that process can be an iterative process where as the design matures, we can continue to do additional design optimization to fine tune various different parameters such as line space, spacing between different layers, etc. So I think the methodology really lends itself to this continuous learning approach, and it also automates the process with some quantifiable metrics that help with making those trade-offs. Based on this methodology that we have developed, here is some initial data that I can share on the accuracy of these models. What I'm showing here on the plot is the predicted versus actual values for yield and cost metrics that we've been monitoring. And you can see that we get very good correlations between the actual data versus our predictions from this machine learning model. To build on that, what we've been able to do is use this methodology for making design optimizations for various products. And here's some data that shows that we are seeing significant improvement in our capacity by following this approach of upfront design optimization and making deliberate choices to balance product performance as well as manufacturability. With that, I would like to conclude my talk about the key vectors that we are seeing. We do continue to see that 2.5D and 3D packaging is blurring the boundary between what is considered as a silicon and package. It is also resulting in the need for optimizing for performance, cost, and capacity, not just looking at it as the best performance product out there. And so the increased design complexity that this brings in of understanding what is needed from a silicon floor plan perspective, what is needed from a package floor plan perspective, and how do we co-optimize all of that really lends itself to machine learning tools. These are not rules that can be codified, but essentially methodologies that need to be developed. And we do see that there is a great need for partnership across the ecosystem to continue to build and evolve these tools. We see the need for heavy engagement from our EDA tool vendors, manufacturing suppliers to collaborate together to continue to fine tune these tools and result in more optimized product. With that, I'll stop and see if there are any questions that I can answer.
Great. There are a few. With the person's commenting, it's insightful and visionary use of machine learning, deep learning, but how general is the machine learning model? Can it cover different substrates or specific machine learning models need for each substrate type? Or, I mean, have you just thrown everything in it for every product, or is it trained for different products or different subsets of your product catalog?
Yeah, that's a very good question. So I would say that the framework that we have developed is very generic in the sense that it can pull in very well-defined design attributes as well as manufacturing data to be able to train and provide these predictions. But within that framework, we definitely do look into optimizing specific models for specific areas. So to that question of if I have different package architectures or if I have different types of historical data, can we fine tune the model for specific applications? Absolutely, we can do that. And in that sense, you could very well have different inference engines running, but the framework itself is very generic.
Right. And, so it's predicting the outcome, but how does that, does the design team then just iterate? Or, I mean, so if you had a classical rule or rule of thumb, you'd know which way to go. But here, how do you know you haven't found a local minimum or maximum? So once you put it in, you get a predicted result. And if you want something better, how do you know which way to go? Or do you have to then submit like 4 other designs and see if one scores higher?
Yeah, that's a very good question. And I think it's an active area of development in the machine learning community in general. I think the way we are looking at these solutions is they do give us a set of feature vectors that tell us key design sensitivities that can provide guidance to the designers on where modification should be done. But the recommendations are not as simplistic as a rule. There can be specific regions where a certain design space needs to be evolved. So in that sense, there are interaction between design parameters that the ML models are able to better predict than just a rule-based approach.
Makes sense. And more about the model. I mean, somebody's asking how willing are the substrate vendors to share their yield figures and affect the different designs or the different parameters? Do you have access to that, or have you had to twist the arms to get that data to feed the model?
I think this is an area where we are continuing to evolve. And the way I would look at this is, as we show more of the benefits of this approach to the extended committee, we see a lot more willingness from various different partners to collaborate with us. This is a net benefit for the industry. It helps improve our designs, but it also helps improve the productivity of our suppliers. And so we do see this as a community effort, not a standalone activity from AMD.
Great, makes sense. Some general questions. Do you have a way that you define the difference between a chiplet architecture and, the traditional or well-established multi-chip packaging, multi-chip module architecture?
Yeah, that's a very good question. And in some senses, as the chiplet architecture has evolved, it has started to encompass the prior multi-chip module as well. I would say maybe a couple of differences. The traditional multi-chip module, while there were scenarios where you had functional die that were separated out. So for example, you could have a chipset along with a CPU in an MCM format. What chiplet does is it is able to also have replications of the same logic element multiple times, right? So the extension of the number of die, as well as the fact that you're replicating that same modular design multiple times, is what I would consider as the big difference between a traditional MCM and a chiplet.
Great, thank you. Thank you very much, Deepak. I enjoyed your presentation, so thank you. And once again, I'd like to thank the sponsors who made this event possible, Advantest and ASC Group. Advantest having high customer satisfaction surveys for over the last 30 plus years from VLSI Research, and the highest ratings in the last 2 consecutive years. So congratulations to Advantest, and thank you to ASC. The chiplet era has begun, and as we've talked, heterogeneous integration will play a vital role in bringing chiplet-based designs to market, and they are working on the advanced packaging technology and working with everybody in the ecosystem to make it happen. The future is heterogeneous integration. And with that, I will thank everybody for joining us and look forward to seeing you at a future MEPTech event. Have a good rest of your day. Thank you.